This is problem 3.18 in Horton's 5th edition. This is the second part. So remember, this question is asking us if we consider alanine, and I will draw it in the normal zwitterionic form here. If we consider alanine, we normally expect to see it in this common zwitterionic form because that's what's going to be most common at physiologic pH. However, one might imagine a unionized form, a non-ionized form, a neutral form, which I would draw like this, and I'm going to call this a non-ionized or non-ionic or non-ionized form. And the question is, what would be the concentration of this at pH 2.4, which is pKa of the carboxylic acid of alanine, at pH 6.15, which is the isoelectric point of alanine, and pH 9.9, which is the pKa of the conjugate acid of the amino group. And so the typical way to draw this, to be clear, would be to imagine this form then, which is the anionic, and this is governed by a pKa of 9.9, and this other form, which exists predominantly at low pH here, and this is the cationic form. And so I did a conceptual approach in part 1, showing you a plot explaining that this is going to be quite rare at all pHs, and how there's an assumption that we can consider, this is pK 2.4, we consider that the amino group, this pKa then describes the deprotonation of this ammonium to the non-ionized form. So this is also going to be assumed to be similar to pKa2, and this is going to be assumed to be similar to the pKa of the carboxylate group. So there's a couple of different ways we can approach this. We can use the Henderson-Hasselbalch equation, which is pH is going to be equal to the pKa plus log base 10 of the unprotonated over the protonated species. And we can use this, so at any pH we can calculate what the ratio here is. So that means if we're interested, for example, at pH 2.4, and we say what's the concentration of this, we can say, well, it's going to be the product of how much neutral amine there is and how much times the concentration of, so the product of the concentration of neutral amine and the concentration of neutral carboxylic acid. And so we can first say, what's the concentration of each of these groups? Well, if we consider this pKa here to be the generic, this and this to be O minus, and this to be the neutral form in each case, we can say, okay, at pH 2.4, let's consider pKa equal to 2.4, that is this. We're going to see that these are equal. So at pH 2.4, the concentration of the carboxylate is going to be equal to the concentration of carboxylic acid. And if I do the same thing at pH 6.15, what will I get? I will see that this ratio has to be what? It has to be a great difference, and this is a log, right? So that means that what's the difference there? It has to be log of what? This has to be equal to 3.75. So log of 3.75 is going to be 10 to the negative 3.75. So 10 to the 3.75 is, sorry, this is going to have to be a positive. It means that at pH 6.15, the ratio of this to this is going to be 10. So there's going to be 10 to the 3.75. The book does it in integer exponents to 1 of the carboxylate to the carboxylic acid, which is equivalent to saying that the concentration, the ratio of the neutral carboxylic acid form to the more common ionized form is going to be equal to 10 to the negative 3.75. So it's going to be quite rare. Likewise, at pH 9.9 plus 2.4, that means log is going to have to be 10 to the plus 7.5, which means 10 to the 7.5 divided by 1, which means that the carboxylic acid form over the carboxylate form is going to be equal to 10 to the negative 7.5. Okay, and for the other group, the amino group, if we want to look at the ratio of the amino group, in that case we're looking at something different, slightly different, but the numbers are going to turn out to be very familiar. I'm going to draw the Henderson-Hasselbalch equation, and this time I'm going to put the amino group above the ammonium group, and we're interested in the above one. So here at pH 2.4, the pKa of 9.9, that means this has to be a log of something quite negative, which is negative 7.5, and at 6.15, 9.9 must be the log of, that's log of 10 to the negative 3.75, and at 9.9 the ratio of the two forms is going to be the log of 1. So that means this ratio, the ratio of the group of interest, the neutral amine, relative to the ammonium group, is going to be 10 to the negative 7.5, 1 to that. So, sorry, let me do it this way. This is going to be, let me use colons so I don't get confused. And 10 to the negative 3.75 to 1, and 1 to 1. So that means that at any particular pH, the group of interest is going to be, let's say at pH 2.2. Let me change pen colors so I can annotate this a little bit easier. I'm going to switch to this blue. So at pH, we're interested in the neutral form. Here, we're interested in this neutral form, so we're going to say at each pH, what's the concentration of neutral carboxylic acid and neutral amine group. So at pH 2.4, excuse me, the acid is half of the carboxylic acid, but the amine is 10 to the minus 7. So that means that it's going to be 0.5. The book doesn't do this quite to completion. This ends with saying it's insignificant, times 1 times 10 to the minus 7.5 times 0.01 molar. And that's pH 2.4. So that's a very, very small number. And at pH 6.5, it's quite similar, because at pH 6.5, the group of interest is 10 to the minus 3.75, and the carboxylate, the carboxylic acid neutral form, and the amino neutral form is also 10 to the negative 3.75. So that means at pH 6.15, the pi, there's going to be the 0.1 molar times 1 times 10 to the negative 3.75 plus 10 to the negative 3.75. So, that's 10 to the negative 3.75 times 10 to the negative 3.75, which is 10 to the negative 7.5. And at pH 9.9, we have something similar to pH 2.2, in which the amino group is going to be half neutral and half ionized, and the carboxylic acid group is going to be a very small number, 10 to the minus 7.5. So we're going to have the same answer here, which is also true at pH 9.9. So that's a very small number. The book concludes reasonably that this is insignificant. Notice that I'm not going for an exact solution here, partly because there's the assumption of what the pKa is of this non-ionized form relative to the cationic form, and the non-ionized form relative to the anionic form is an assumption, and that assumption is the accuracy of the assumption is quite a bit looser than we would ever care for these numbers to be, because 10 to the negative 7.5 is an insignificant number for this form. So notice also that despite the very wide change in pH, the concentration apparently varies maybe not at all or only slightly. So as I showed you in the earlier plot, I can show how one form drops, the zwitterionic form comes up, the zwitterionic form comes down, and the anionic form comes up. The form of interest here, which, if you will allow me to follow my pen color change, the form of interest for us is very, very low throughout, and it doesn't rise and fall. It's pretty much steady, 10 to the minus 7.5 relative to the other forms. So it's multiplied by the concentration. So it's quite low. Notice that the book answer doesn't explain why the assumption is poor. That's doesn't really matter, and it doesn't go to a final calculation. It just concludes that the concentration is significant. It also doesn't use fractional. It also doesn't use fractional exponents, which are easier to handle. We could also directly work with Kas rather than pKas, which would make it simpler, but it's nice to use the Henderson-Hasselbalch equation. And the book has a very confusing thing where they have 4 different species, but they show a ratio of 5. Don't let that confuse you. The first number should just be deleted.